Hello, my favorite people. So in our lesson 2 today, we're going to take a look at something called the first derivative test. And it really is just continuing our conversation from lesson 1 about increasing and decreasing functions and trying to find those local min and maxes, okay? One of the things we said with Fermat's theorem was that a local min or max had to occur at a critical value. So remember that a critical number is where the derivative either equals 0 or the derivative was non-existent, okay? Now, the other thing we said, though, was that it didn't work the other way. Not everything that was a critical number would come out to be a local max or min. So we need to somehow solidify, go a little bit deeper into our understanding so that we can look at those critical numbers and we can decide whether we do in fact have a local max or a local min, okay? And really we pretty much, we almost just did this already with increasing and decreasing functions. We just want to kind of put a more solid form to it today, okay? So recall, not all critical numbers are maximum and minimum points. I've shown you the graph here. Actually, I'll hide myself for a quick sec in case I'm messing up that graph. That is the graph of f of x equals x minus 2 all cubed, okay? The derivative of that is 3 times x minus 2 squared. Now, x minus 2 is a critical number, but it's not a maximum or a minimum, okay? And if you want to check that, what we can do is we can plug in x equals 2 into the derivative, and we would in fact see that the derivative at 2 is 0, okay? But again, I'm going to hide myself for a second. When we're looking at 2, we know for sure that that is not a local max or min point. Actually, that's a point of inflection, okay? So even though it's a critical number, it's not a local max or a min, okay? So what we need to do is we need to figure out a way to tell whether it's a local max or min. So if the derivative of f at 2 is 0, and one might expect a max or min value, but it isn't when we look at the graph. Remember, part of all of this is we want to be able to do this without looking at a graph now. Okay, so we need a method to determine which critical numbers define maximum and minimum values. And we do that by looking at the derivative on the left versus the derivative on the right. And that's why I said we essentially just did this in our first lesson. We just didn't call it the first derivative test. How is the derivative behaving before and after x equals 2? Okay, so are the derivatives positive, negative, or 0 for the following? So we're going to look at the derivative of 1, the derivative of 2, and the derivative at 3. Okay, so go ahead and do that. Maybe pause me for a second. I don't care what the actual numbers are. I care whether they're positive or negative. Okay, and so what you should have seen there is we ended up with positive on the left, then the 0 at 2, and then positive on the right. So your big take-home message here is we didn't switch, okay? The signs did not switch. I went from a positive derivative to a positive derivative, okay? Where I'm going to get those local min and maxes is when I switch signs for the derivative. So now take a look at this guy. Again, I'm just going to hide myself for a second so those of you playing along at home can see the graph. Okay, and so we want to think about 2. And we want to think about the derivative of 2. So we want to look at the derivative at 1, the derivative at 2, and the derivative at 3. So again, just think this through for a second. We know the derivative at 2 will be 0 because the tangent there is a horizontal line. We know the derivative at 1, ooh, that was bad, but that will be positive. And we know the derivative at 3 will be negative. Okay, I'm just drawing the tangent lines there so we can decide whether the slope is positive or negative. Okay, so here we have an instance where on the left, my derivative was positive. At 2, my derivative is 0. And then on the right, my derivative is negative. So I've switched signs and I do in fact see a local maximum in that original graph. Okay, so what do you notice about the derivative as it passes through the critical point? The sign of the derivative changes. That's the first derivative test, okay? If we check to the left and to the right, the derivative sign should change to the left or to the right of a critical number. If it does, then we know for sure we have a local max or min, okay? So considering the graph of any particular function y equals f of x and the behavior of the derivative of f of x as it passes through that critical number will determine whether or not the critical number is at a maximum point, at a minimum point, or neither. Okay, and so we're just going to give an algebraic definition for each one of those. You have this gray box in your workbook that you're going to fill in with me, but I've also created a picture for each scenario just to try and help you visualize what's happening, okay? So the first guy, so if A is less than C is less than B, which just means the point C is in between A and B, which I've shown you on the graph here, okay? And C isn't the X value of a critical number. So if f of C, or f of C will be a local maximum if the derivative of A is greater than 0, so it's positive, and the derivative of B is less than 0. Okay, one might think of this as the derivative changing from positive to negative. Okay, and what I want you to see here, pink is the original function, and then the blue line is the derivative. So we can see at C, the derivative is changing from being positive to being negative. Okay, so if the derivative changes from being positive to being negative, we found a local maximal. Okay. The reverse of that, if the derivative changes from being negative to positive, so take a look at this. Okay, again, the pink is the original graph and the blue is the derivative. So if the derivative changes from being less than 0 to being greater than 0, okay, then we have found a local minimum. And then if the derivative sign doesn't change, oh, sorry, I didn't finish that statement. One might think of this as the derivative changing from negative to positive, okay? If the sign of the derivative doesn't change, so in this example, you can see that my derivative is positive leading up to the critical number, and then my derivative remains positive after the critical number, okay? So so that means there's no maximum or minimum if the derivative does not change sign before and after the critical point, okay? Okay, so let's try a question together where we put all this together. So determine all the maximum and minimum values for the function f of x equals x cubed times x minus 2 all squared on the interval -1 to 3. So the first thing I want you to notice is I said all the maximum or minimum values. So that's going to include both local and absolute, okay? And in your conclusion, you're going to need to make a distinction as to which ones are local and which ones are absolute, okay? And it's over an interval, so I'm also going to want to look at -1 and 3 in as well as the critical numbers, okay? So to get the critical numbers, the first thing I need to do is figure out the derivative. And so when I'm looking at this, the easiest way to handle the derivative on this, I think, is the product rule. So I'm going to go derivative of f times g plus f times derivative of g. So derivative of f will be 3x squared times g, x minus 2 all squared. Then I'll go plus fx cubed times the derivative of g. Now the derivative of g would be the product rule, or sorry, the power rule. So I got 2 times x minus 2 to the 1 times the derivative of the inside function, which happens to just be 1 for this guy. Okay, so now what I'm going to do is I'm going to factor out what I can from these two terms. So I've got a term here and I've got a term here. Both of them have at least an x squared, so I'll factor out the x squared. The guy on the left here has an x minus 2 squared, and the guy on the right has an x minus 2. So I'll factor 1 x minus 2 out as well. Okay, so when I go and do that factoring, I took out the x squared, and that's going to leave me with 3 times x minus, sorry, I took out the x squared and the x minus 2. So on this guy, the first guy, I'm left with just the 3 and 1 more x minus 2. And from the second term, I'm just left with 2 and x. Okay, so now I want to clean this up a bit. 3x minus 6 plus 2x, and then that'll be 5x minus 6. Okay, so the derivative of f is x squared times x minus 2 times 5x minus 6, okay? Now, I need to think about the critical numbers. Well, the critical numbers are where the derivative equals 0 or the derivative doesn't exist. There is no opportunity in this particular function for the derivative not to exist. It exists on all values of the domain. But there are 3 opportunities for the derivative to be 0, and that would be at 0, at 2, and at 6 over 5. So my critical numbers are at 0, 6 over 5, and 2. And then I know I have my endpoints at -1 and 3. So what I now want to do is take those 5 items and stick them on a number line, okay? And that essentially brings me into 1, 2, 3, 4 areas that I need to check to see whether the derivative is positive or negative, okay? So for each of those areas, you want to pick a number that exists in that area. So like that first one I circled, you want to pick something in between -1 and 0. You want to plug that into the derivative equation and see whether you get a positive answer or a negative answer. Okay, I want you to do that for each section. Pause me, do it, and then you can start me up again. Okay. Okay, and what you should notice is we ended up with a positive region here, a positive derivative here, a negative derivative here, and then a positive derivative between the 2 and the 3. Okay, so remember, according to the first derivative test, I'm going to have a local max if I switch from an increasing to a decreasing derivative, so a positive to a negative. And I'm going to have a local min if I switch from negative to positive, okay? So I know that I have a local maximum at 6 over 5, and I know that I have a local minimum at 2, okay? All right. I know the other ones are not local max or mins because I don't switch signs, okay? But now I need to figure out the y values that go with every one of these 5 either critical numbers or endpoints, okay? Because it's the y values that will now ultimately determine what the absolute max and what the absolute min is. Remember, the absolute max and min have to either come from the critical numbers or the endpoints. So now I want you to pause me and I want you to find all the corresponding y values, okay? Okay, so you got that, lovely. So we also want to state where this function is increasing and where this function is decreasing, okay? So I want you to notice I am increasing from from -1 to 0, and from 0 to 6 over 5, and from 2 to 3. Okay, so that'll be like 3 different sections in union with each other. And then I'm decreasing from 6 over 5 to 2. So the first thing I've stated was I'm increasing, this is just what I said, increasing from -1 to 0 in union with 0 to 6 over 5 in union with 2 to 3. Then I'm decreasing from 6 over 5 to 2. You already have your y values for those 5 numbers and they are right here. So now we want to just compare. Just in case my big old head is in the way there, I'll hide for 1 second. I'd go -9, 0, 1.11, 0, and 27. So I know my absolute maximum is going to be here at the 27, and my absolute minimum is going to be here at -9. Okay, so now I just conclude everything I've just said. So I've got an absolute max, I've got an absolute min, I have 1 local max, and I have 1 local min. So I put all that together in my conclusion. So I have an absolute maximum at f of -1 equals -9. Sorry, I said maximum there. I have an absolute minimum. I should listen to myself more often. I have an absolute minimum at f of -1 equals -9. I have an absolute maximum at f of 3 equals 27. And then from that number line where the derivative switched signs, I realized I had a local minimum at f of 2 equals 0, and a local maximum at f of 6 over 5 equals 1.11. Okay? So I have been able to conclude completely algebraically, without ever looking at a picture of this, I have been able to conclude where all my maximum and minimum values are. I also know when the function is increasing and decreasing, so I could plot those max and min points with an understanding of where I'm increasing and decreasing, and I could actually draw a pretty decent sketch of what this graph would look like, okay? And it would look something like this, okay? And so I'm increasing from -1 to 0, from 0 to that 6/5. Then I'm decreasing from 6/5 to 2, and then I'm back to increasing from 2 and beyond, okay? Now, I wanted to show you the levels of increasing and decreasing here. So I haven't actually shown you the point -1, -9. I haven't gone down that far. And I haven't actually shown you the absolute max up here, B3 at 27. But I wanted you to see those increasing and decreasing levels better than had I made the picture bigger, okay? All right, cool. So that's what you're going to do. Your homework, your mission, should you choose to accept it, and you have to, is here. If you have any questions, though, please make sure you're connecting with me, okay? And next up, after this guy, we're going to start talking about applications of max and min. Okay, take care, guys.